Welcome, everyone. We are happy to have you here. We are about to get started. There are more people trickling in, so we'll give a few moments to those that are coming in as we get started. While we wait, we'll introduce the topic today. I am Chase Fly. I am with Delair, and we are based in Toulouse, France. We have been making drones and the drone industry, the commercial drone industry, since 2011, and even before with some of our partners and subsidiaries. So we're happy to announce today the DT26X LiDAR product. This is a product that we've been working on for some time, and it really enables you to get twice the data in half the time. We've focused a lot on making a more sophisticated, more useful, more productive payload, and that's what we're introducing you to today. And that payload includes both a LiDAR and a photogrammetry sensor. So the presenters today will be myself, Chase Fly. I'm the Geospatial Product Manager at Delair. And then we have our colleague from RIEGL, and I'll let Philip introduce himself.
Yeah, thanks, Chase. My name is Philip Amon. I'm a Business Division Manager for unmanned laser scanning at RIEGL Laser Measurement Systems in Hohen, Austria. I'm responsible for our whole unmanned products, including our minivux and VX1 series, as well as the platforms and payload integration. So all with regards to unmanned systems.
Fantastic. Thanks, Philip. And from my end too, just so you know, as part of Delair, we work on both hardware and software systems related to drones. And so my role is to work with our development team as well as our sales staff to ensure that the products we are developing fit the needs of customers. So always open to hear ideas and feedback from our customers as well. A little bit of housekeeping to get started, and we're going to kick this off with a little poll to get you familiar with this webinar platform we're using. There on the right hand side of your screen, you should see a kind of a white box, or at least it's a pull-out bar. So there's an arrow in the upper right that you can click on if it's not displayed, and you can click on it again to hide that sidebar. But in that sidebar, there should be a questions tab, a polls tab. And in the questions tab, you're welcome to submit questions as we go along. Those questions, we will save some time for at the end to respond to a few of those. If we don't get to all of them, we'll get back to you at a later time. You can also look at those questions, and if you see someone has already asked a question that you have, you can like that or upgrade that so that we kind of see the ones that people have most interest in raised to the top. And then polls will be launched like this one. So my colleague has launched that. You should see under the polls tab the question with some answers that you can click on. And so in this case, why are you interested in a LiDAR and photogrammetry drone? You can select, I need a solution for a specific project. I need to collect data on a regular basis. I'm interested in expanding my fleet, or I'm just curious about the technology. So please feel free to participate. We'll try to take these into account as we go along here and make sure that we are addressing your needs. So without further ado, let's jump into it. The DT26X LiDAR is really a UAV, or an unmanned aerial vehicle built to scale. What we mean by that is it's a product that's really built for those large-scale projects from the perspective of a typical drone operator, or maybe on the small scale from the perspective of a manned aircraft operator, like a helicopter operator or something. But really, it fits those medium-sized projects on the grand scheme of things, but it allows you to do a lot of mapping in a little time. And we do that because we've got a fixed-wing platform that's very efficient in flight. It's equipped with multiple sensors. It's a high-endurance machine. And it's got extended range communication systems so that we can really tackle those large scale and long range mapping projects. The goal behind the Delair DT26X LiDAR is really to help businesses and organizations reduce their costs of collecting LiDAR. It's also aimed to provide access to LiDAR on more projects. There's a lot of projects that I'm sure you've seen come across your desk where it's either too expensive to be to deploy a manned aircraft operation, or it's too unsafe or too risky, or will take too much time to do on the ground with traditional terrestrial survey methods. So this is really trying to tackle those areas where you're not able to efficiently get the job done. It provides that scalable alternative to a manned aircraft for corridor and large area mapping. So to talk about the payload a bit, the payload is fully integrated, but it's plug and play. So our DT26 UAV actually allows you to use a few different payloads, and you can swap between them if you needed. But the one we're focusing on today is our LiDAR payload and photogrammetry payload. So it really combines three main components, which is the RIEGL minivux 1 DL sensor, LiDAR sensor, which is a downward-looking version of the minivux that they've previously developed. And we'll talk about why that's important for our particular system. We use the Trimble or the Aplanix APX-15 UAV GNSS IMU board. That provides very high accuracy GNSS data or position data, as well as orientation with the advanced IMU. And then we use our own Delair developed camera. So we've got an RGB camera fully integrated into the system that allows us to collect images at the same time we're collecting LiDAR. All of that data will be stored on board. So what that gives you is an equation that usually wouldn't make sense. 1 + 1 + 1 = 1. We have a Delair fully integrated camera, industrial grade camera. We have the RIEGL minivux 1 DL LiDAR sensor, and the Trimble Aplanix APX-15 UAV sensor, all built into our Delair DT26X LiDAR system. So this really aims to enable you to do more with less. There's often constraints on budgets, constraints on man hours, even human resources at some stages, and this platform allows you to be more efficient with what you have. And the ultimate goal of integrating both sensors together, the camera and the LiDAR sensor, is to be able to do true LiDAR point cloud colorization. The point cloud you see here is a standard point cloud, but a true colorized point cloud offers an added value to the standard point cloud that just has the height info by allowing for easier classification or stratification of the point cloud data. It also enhances the visualization and 3D models that are produced. And further, colorized point clouds may allow additional analysis or modeling based on the color value in addition to the elevation data, such as for applications like species classification. So you can start to think about using the data collected from this drone for a lot more than maybe you would have used only LiDAR or only photogrammetry, or maybe where you would have flown 2 drones to accomplish the same thing, or a much more expensive manned aircraft operation on a small project where you have the need for both data sets. So standard LiDAR outputs are certainly useful, like this one. It can yield beautiful results in themselves, including the ability to stratify vegetation classes and bare earth. But being able to see things as they really are is what LiDAR combined with photos enables. Being able to get that real-world 3D modeling data set. And with the DT26X LiDAR, we are able to achieve as good as 1.7 centimeter GSD orthophotos at only 120 meter flight height. So that's 400 feet. That's a standard flight height by regulation in most Western countries, as well as many countries elsewhere in the world. And so we can get a very high level of precision that really fits the realistic use case operating within the regulations as they are today, to get good data and good data, both photogrammetry and LiDAR. So not only do you have multiple elevation values for each horizontal coordinate, but you have the accurate colorization of that point cloud and your stratification of vegetation and other benefits of LiDAR. So let's launch another poll, and we'll give you a few moments to look at this. What type of project areas are you most likely to map with this system? Are you most interested in cover zones, such as polygon-shaped areas, corridors, such as linear projects, maybe infrastructure, power lines, etc., or some of both? Go ahead and put your answers in, and we'll keep an eye on the results. Then we're going to do another one right after that, a second poll right in a row that's related to the first. Which features are you most interested in mapping with LiDAR? Power lines, other infrastructure such as roads or pipelines, vegetation, trees, crops, low-lying plants, or other objects like buildings or landsides, or do you just want the bare ground? That's kind of what we're trying to tackle here, and trying to understand a bit more what you guys are interested in doing. Feel free to keep your answers coming on as we go through there. Okay. Thank you very much. Keep going. Keep punching those in if you want to think about it. Yeah, I think they should be up throughout the webinar. And then now I'm going to turn the time over a few minutes to Philip here, who's going to go into a little more detail on the RIEGL minivux 1DL sensor itself. Philip?
Yeah, thanks, Jace. Yeah, I would like to just talk a little bit about the scanner itself. It has perhaps already been mentioned. The DL itself, it stands for downward looking. The weight of the sensor itself is 2.4 kilogram, and combined with INS GNSS system, this has already been mentioned by you, it ends up with a total payload integration of around 3.2 kilogram with the Planix APX15. The downward looking has been especially designed to meet the requirements for corridor mapping projects, such as mentioned here, pipeline, power line monitoring, highway and railway inspection. And we do get the 100 kilohertz, so the pulse repetition rate, down to the ground by measuring up to 200 meters by around 60% of target reflectivity. And to give you a little bit better overview about how the pattern works, I hope we can play the video that shows the rotating wedge prism in detail. Can you just show up the video?
Yes, let me pull that up.
So I hope this runs smooth. Like this video shows very short how this rotating wedge prism works with the circular pattern with 23-degree off nadir, so covering the 46-degree in total. And it brings the whole pulse repetition down to the ground and increase at the end the point density compared to the other products. So you do not shoot the laser shots in the air, you get like the whole pulse repetition rate down to the ground. Yeah, as already mentioned, we have a field of view of around 46 degree, means plus minus 23. The scanner or the rotation speed itself can be measured up to 75 times lines per second. And this rotation speed is changeable and it provides like an almost uniform point pattern when changing the speed, especially in nadir. And as you can see, we have taken out here 3 examples from different flight altitudes, 80 meters, AGL, 100 and 120 meters. And even the scanner's flight altitude is given by around 80 meters. The flight altitude of the UAV can be much higher than that, especially when like your target or the target of your project is covering only the power line and you're not interested as much in the terrain below. As an example here, when we fly 120 meters AGL, the resulting swath width on the ground is around 100 meters, and you gain around 35 points per square meter, covering around 10 square kilometers in one single flight. So this is already not that bad. And to give you an information also about like the technology a little bit behind, if you jump one further, Chase, to show you this multi-target capability. So RIEGL provides very unique echo digitization and this online waveform processing, which makes it capable to get multiple returns from one single shot to cover first target and intermediate targets in between, so that you get like the true ground, the lowest target as well. The limit is up to 5 targets, but this can be easily been reached. So you would have like here 1 first return target on top, 3 intermediate targets, and 1 laser shot at the end, which should be, of course, most important, the ground point at the end. To give you just some ideas how the data look like, this has been data captured with the DL. We see here data colored in flag-10s and in different view types. If you jump one further, it's a couple of screenshots where data also from a forward and return flight has already been combined. You see that on the left and right hand side there's no data, but this is resulting to the 46-degree limiting field of view, but this should be almost enough for covering like the power line and the surrounding areas. And if you go one further, yeah, here as well, the power line itself is being covered, so it's being marked as well, and especially when it goes further than when extracting data. Like here, it's being shown. We have an image on the left-hand side. We have the image combined with the point cloud overlaid in the middle, and at the end you have the resulting CAD model. So which means we export from the software georeferenced point cloud, georeferenced image, combine this in third-party software. Like here, this was done in Topodot, but could be done in similar software packages as well to extract further information from the power line. Of course, it was mentioned by Jace already, the color information itself, by coloring the point cloud, would also be an option. So far from my side, giving you a little bit details about the sensor itself. I think Jace, you will proceed.
Yes, thank you, Philip. So the second part of our payload, the LiDAR being sort of that core jewel that we're so proud of, but then we have our Delair HD camera that we've been developing for some time that we are very proud of as well. The camera that we've integrated is an industrial grade sensor designed by Delair, including the data processing on the back end, the way the images are handled, and the way that the connection occurs between the drone and the ground control station on the ground. So what that allows us to do, having a real-time camera link, because our camera is fully integrated into the electronics, that allows us to do things like quality control on the fly, adjust camera settings and parameters while it's in the air. A lot of the drone solutions you find out there use off-the-shelf cameras that are triggered by USB or infrared, and you have no visibility on the data until it lands. But we have visibility on the data throughout the flight, and we can adjust as needed to ensure that we're getting good quality data. That way, when you land, you know you've got photogrammetry ready data. You're not guessing whether it's good or not. So being able to control those camera settings, having a decent resolution camera such as this 21 megapixel camera, we use a true global shutter is critical to ensure that we eliminate any aberrations or lack of precision in the images. And then we are able to produce down to 1 centimeter GSD imagery if we desire. And that's based on flight height, of course. Another critical piece, so the Planix board we use, the APX15 GNSS IMU board, is a dual frequency GNSS sensor. We do use PPK. We don't use an RTK connection. We have many reasons for that, but we can get a more robust correction when we do PPK versus RTK. So there was a question on that came in, so hopefully that addresses that. We use PostPack to do the post-processing of both the GNSS positions as well as the orientation or the IMU, the angles produced by the IMU. So it's a direct geopositioning system, and that means that we have precise positioning both in the GNSS and in the angles, but it is not a full direct georeferencing system that would involve a calibrated camera and so on. You can calibrate the camera, however, so you can get very close to that. and that is, but it does produce very accurate imagery, down to 5 centimeters of accuracy if you were flying at a lower height perhaps. But a very real world example is at about 120 meters, we can get plus or minus 10 centimeters and often better. But that's just to give you a very realistic sense of what sort of data this system can produce. Of course, you've got a lot of high-end sensors and technology in this drone that you're throwing into the air and that must come down and land at some point. So we want to emphasize that this entire airframe is designed for a safe belly landing. And the belly landing is very controlled compared to many. We even have the ability to manually flare the aircraft as it touches down. So the touchdown is very soft. It does not skid for a long ways. It's a very smooth landing, and we've done dozens of flights with high-end sensors without issue. So we're very confident in the way we've developed this. And the way we protect that payload is first with an internal composite backbone structure. So it's a very rigid, very high-end but lightweight, strong material. So that creates a bit of a box around it. And then we have the outer composite shell, which is a composite design of multiple layers such as Kevlar and fiberglass and so on. And then we have a collapsible foam bumper on the bottom. That is a replaceable part as needed, which is not frequently, but it is something you can replace, and it absorbs any shock that it might occur if it comes down and you have to land it on, say, a harder surface as opposed to grass. So that helps protect it. And that sensor and payload itself is recessed into the drone, and that's one reason this downward looking, the DL sensor, works so well in our system, is because that allows us to recess it and have it fully protected while it's in flight. So we're very confident about how that is packaged in there. It's all, when you have a high-end system like this and sensors to boot, you really want to be able to get a lot of work done. So the DT26X allows us to fly farther and longer. We have long-range communications up to 20 kilometers over radio, and that's with a directional radio I'll show you here in a moment. And we have virtually unlimited communications over our secondary 3G communications option. And that is very unique and opens you up to a lot of true beyond visual line of sight operations. That, combined with being able to fly for nearly 2 hours, up to 110 minutes, really opens the door to a lot of complex and missions, as well as straightforward missions, but being able to get them done in an efficient way and getting a lot of work done at a time in a single flight. So just a quick look about how those communications work. So on the bottom right here, you see what we call the Mama Bear radio. And this is a directional radio that will track the DT26 while in flight. It gives us both C1 and C2 connection, meaning we get command and control of the aircraft, and we also have a data connection. So up to 20 kilometers, 15 to 20 kilometers in typical terrain and even mountainous terrain, and even farther than that, up to 30 kilometers if you're flying at higher altitudes or have very clear line of sight. But then, and then you have a Wi-Fi connection between that radio and the ground control station, which runs our SOLAP mission planning software. And then there's a 3G option, which is a machine-to-machine network that we've established, that we manage. There's a SIM card built into a modem in the drone, and then you have one you put on your ground control station, and that establishes a secure network that you can command and control with as well. So with that option, you can really operate just about anywhere, provided you have cellular service. So another quick poll we'll launch. Which feature of a LiDAR mapping drone is most important to you? Are you most interested in the characteristics of the UAV itself, the quality of the LiDAR sensor, the fact that there's a dual sensor payload for photogrammetry and LiDAR, or is price of most importance to you? Interested to hear your feedback there. All right, we'll start to close here, and I just want to give you an idea of how productive this drone can be in a day, so you can begin to imagine the types of projects you might be able to do with it. We split this up looking at corridor projects versus kind of a cover zone or a polygonal area type project. But in one day with one operator and operating at 400 feet or 120 meters, the typical flight height, legal flight height, I should say, you can very feasibly do 3 flights in a day, maybe more, maybe less, but 3 is about average in talking to our experienced operators here. So on a corridor project, that's going to yield up to 120 kilometers or 75 miles of a linear feature. And on a cover zone project, that's going to go up to 29 square kilometers or 11 square miles. That's a lot. Compared to most drones mapping in a day, you're getting a whole lot of work done. However, if you are using a helicopter or other manned aircraft, you can get more than that done, of course. But the question is, where does the cost benefit come in? And that's just what we want to kind of give you an idea of here. We know ground surveys are expensive when you look at man hours and time. For smaller projects, they often make the most sense. They can yield the best precision. There's all kinds of reasons that we love and need ground surveys, and that's not going anywhere. On the other end, you have manned aircraft surveys, which are for larger scale projects. So that might be when you've got 1,000, 2,000, 3,000 kilometers of power line, you need a survey. The cost can become quite affordable when you look at it per unit, down per square or per kilometer or per mile of linear feature. However, there's usually a pretty steep mobilization cost. So there's this kind of area in the middle between ground surveys and these manned aircraft LiDAR surveys where it's too expensive to deploy or mobilize a manned survey or an aircraft survey. It's too expensive or unsafe to deploy, or will take too long to deploy a ground survey. So, or maybe weather and other things impact either of those options where a drone can get around some of that. So it's clear that the Delair DT26X LiDAR fits a certain profile mapping project based on scale and cost. And that's really what we want to emphasize here. Those other tools aren't going away. We're not replacing them outright, but we know there's a place in the middle where this tool is useful, and we hope you can see where that might fit into your workflows. We'll ask you one more question here about the size of average project area you would like to save money and increase efficiency with the drone LiDAR solution. So what size of project do you imagine this working for you? And we split it up there by corridor and cover zone. A 0 to 40 kilometers of corridor, 0 to 10 square kilometers of cover zone, 40 to 1,000 kilometers of corridor, and so on. So if you want to take a look at that and pick what seems to be the best fit for you, or what you most need to do if you really do need those large scale projects and hoping to do it with the drone, we're interested to hear that as well. And lastly, we'll launch this poll just to see where we go from here. We hope you've gotten some information out of this webinar. We've appreciated being able to present this product to you. And how would you like to learn more about the Delair DT26X LiDAR? Are you interested in a more technical webinar where we go into more of the specs, maybe some data, an application-specific webinar for forestry or your industry, a live flight demonstration in your region? Would that be of use to you in evaluating a product like this, as well as white papers, sample data sets, and so forth? You can select multiple. We're interested to know what you want to see on this. And to announce, for those of you in the US or anywhere near or anywhere else that want to take a trip there, we are looking to do a demonstration flight in the Portland, Oregon area here next month. So if that might be of interest to you, let us know. Reach out to us through this webinar, through a question in the question box, or through my contact here, and we'd be happy to get you on that invite list and see if you're available to come out. With that, we're wrapped up with the webinar piece, and there have been several questions. So let me see if we can't get to answer a few of those. Let me sort them. Okay. All right. Looks like Philip took care of a couple. One that had a lot of interest was, do you have a solution for the calibration and processing of point clouds, and what is the accuracy of the system? And Philip is correct. Typically, when we deliver this system, we include, or our customers already have, reprocess from RIEGL, which is a post-processing software suite. You'd also use PostPack from Planix, which is a software suite to correct your trajectories and your GNSS data. So that all of that coming together can produce very high precision in your point cloud, plus some precision in your GNSS and your positioning, and then if you put in control, you can get even better, right? So without any control, we kind of put out there that plus or minus 10 centimeters is very realistic. You add control and you can get even better than that. Is it possible to have a live view of the point cloud? Not today, not on the last few minutes that we have, but we can certainly do a follow-up session and get you some sample data and or we can provide that demonstration as well. So let's follow up on that at another time. Ground control points required per flight. That's the golden question. Everybody wants a golden answer. That is a tough one. Ground control points are always a good idea, always recommended. I've heard multiple rules of thumb, but they're all different and none of them are perfect. So I won't give you a direct answer to that, and I apologize for that, but suffice it to say that ground control is always recommended. And if you're doing a corridor project, there are good patterns that are recommended, such as a staggered pattern, left and right. Let's say every quarter mile would be a very dense GCP configuration, and maybe every mile on a linear project might be a more spread out configuration. So depending on the goals that you're trying to achieve with that project, you're going to need to make that determination. In a cover zone, always good to have a few to use as checkpoints, and if you've got very variable terrain, having a very dense GCP configuration is going to be a great benefit, but you can certainly do with just a few, say, I don't know, 5 every well, let's just say 10 every square mile, but that's no scientific rule of thumb. That's just one guy talking. So there's lots of ways to go about that.
Just let me jump in for 1 second. When it goes to ground control points, we do have in RIEGL process pretty new some feature extraction, some automatic extraction of ground control points, especially if you have a predefined pattern. But perhaps we can cover this in one of the next technical presentations to give you a little bit more details about that, and also decrease the time out in the field to get used to this ground control objects. Of course, we also recommend to have it if you would get the customer or your customer the best data at the end, then it's no way, you have to use it.
Excellent. Thank you, Philip. I just answered a question on the GNSS and RTK. Is it possible to have a live view on the point cloud? That is a feature that we are developing into, we are looking at for our ground control software. So there are possibilities for that with our communication system. More on that later. Possible to have, is LiDAR multispectral? How good is it? As Philip mentioned, the wavelength is in that near infrared band. So that allows for great penetration of vegetation, but it may also allow you to pull that data, that infrared reading from the point cloud itself as a fourth band to the RGB that you get from the photogrammetry. So that's something that could be considered and would be a very interesting for us to hear about your applications as well. I see the plus or minus 10 centimeter accuracy at 120 meters. What flying height do you need to be at to see 5 centimeters? To get you a real answer on that, I'd want to confirm, double check, but I would suggest or suppose that would be around 80 meters flight height, which is also 80 meters is the optimal to get the strongest returns from the minivux 1DL, and that's going to get you great photogrammetry data as well. But if you're doing some tall structures, or, trees or power lines, flying higher than that means that your target is going to be probably within that 80 meters. So it's going to depend on what you're doing, right? But to get that higher accuracy without any ground control, you're going to need to be pretty low. I would suggest you go the ground control route and try to tighten it up that way.
Just to let me jump in once again, the 10 centimeter plus minus, I think, is especially due to the Aplanix APX15. The sensor itself has a different accuracy and precision, so the repeatability of the measurement, it's 15 and 10 millimeters. Means like the single measurement itself is 15 millimeters accurate. Of course, it combines with the INS GNSS solution, and of course this may result in a worse or quality. But of course, ControlPoint would solve this problem a lot, and even like this right precision module in right process that adjusts the trajectory based on the point cloud would give you much more value out from the point cloud. Or accuracy at the end, of course.
Thank you. Yes, very good answer. That 10 centimeters is something is just kind of a ballpark to give you an idea of what you can see in the final deliverables on, let's say, a terrain where there's a lot of vegetation and a lot of other features that, and this is combining your photogrammetry looking at your photogrammetry accuracy as well. So there's a lot of room to adjust in there. Several other questions in here, pros and cons. I think we are over time. So what we will do is we're glad to see so much participation and so many questions. We will respond to those offline, either individually or maybe we'll put together a document we can distribute to those of you who attended that you can see. So we will get back to you on the remaining, and we are grateful for your attendance. Hope you've learned something, and we appreciate your time today. And we look forward to following up with you and seeing how we can further educate you on this new product. Have a great day.
Thank you very much.